Okay, it's my pleasure to announce our next speaker, Dr. Jesse Morris, who is currently a postdoctoral fellow at the University of Idaho and Kansas State University. He received his BA degree in geography from the University of South Carolina and Columbia, and his MS and PhD degrees from University of Utah down in Salt Lake. Dr. Morris is broadly interested in how forest ecosystems respond to climate and disturbance, particularly native insects, logging, and wildfire. And today he's going to give us a long-term vegetation perspective for the Colorado Plateau. So let's welcome Jesse.
Thanks, Justin. Hi, thanks for being here right before lunch, sticking around. So what I'd like to talk about today is as a paleoecologist, to provide a longer-term perspective to some of the problems and issues that have come up today. Thinking about the way that disturbance interacts with ecosystems and different plant types. Mostly I'm going to be talking about subalpine systems, so this is 3,000 meters or above down in southern Utah, which this sort of oblique image here, you can see the Great Salt Lake, and we're just to the right of that, and then down here is the Colorado River, and so we're going to be talking about these whitish peak landforms down there. Okay, so first thing I'm going to do is kind of go through why I think the past matters and why it's important for resilience, for restoration, for thinking about the long term, the future prospects of these forests. And then talk a little bit about the paleo tools and methods that I used and other paleoecologists use to sort of provide this background or this context. And then I'm going to talk mostly about disturbances, as you probably deduced from the opening slide. It's mostly wildfire, and then a little bit about spruce beetle outbreaks, southern Utah, and then sort of consistent with the theme of the workshop, just try to hit on these ideas of stability and resilience, particularly in these higher elevation forests, which by some measures are particularly susceptible to changes in climate and disturbance regimes. So Colorado Plateau is right here, and so again, most of the places I'm going to be talking about are these highlands right there. Okay, this is kind of a cartoon of the Earth's history, and no matter how many times I tell my relatives what I do as a paleoecologist, they always ask me about dinosaurs. Don't look at dinosaurs at all. This is way down. This is 4 billion years of Earth's history, but right up here, mostly at the top, this is the Quaternary period, or about the last 2 million years or so, and that encompasses all the Pleistocene and the Holocene, a little bit of the Pliocene. And so what's going on there, what makes the Quaternary important, is that this is where we start to have ice ages, and this is where Homo sapiens become increasingly important towards modern during this period. So that's mostly how I'm going to frame this. No dinosaurs or anything like that, or evolutionary scale of history. But the late Quaternary is a pretty exciting period, particularly in North America. Okay, we have a lot of things that went extinct. This is, I'm talking about the last 15,000 years. There was a species of spruce in the eastern U.S. that went extinct. Some of Steve Jackson's work. We have these charismatic megafauna that went extinct all throughout the continent, including Utah and in the high elevations. There are mastodon and mammoth remains that were found. The Wasatch Plateau and the Markagunt Plateau. So over longer time scales, these extinctions are certainly playing a role. And then finally, the other point, another extinction is ice out of this area, and the extinction of inland water bodies, particularly Lake Bonneville, and some of these others that certainly modulated or regulated climate in these regions. And if you think about ice, this is T0. This is where nutrient availability, where these ecosystems were born, that I'm going to be talking about today, 10, 12,000 years ago. And so that's the entire history of these landscapes is what I'm going to be talking about. So this is a cartoon from Russia. This is some work I'm involved in over there, but I think it pretty nicely articulates what is happening over the last 10,000 years. So you can think of the early Holocene up here in this top panel is 10,000 years, and this is applicable for a high latitude or high elevation site. There's greater seasonal contrast. The solid line is summer insolation. The dashed line is winter. And so in the early Holocene, there are greater seasonal contrasts that we know this from how our Earth orbits around the sun and these sort of slow processes that control how much energy we receive at the Earth's surface. So early Holocene, you can think really warm summers, cold winters, and as we move towards present, you can see this movement of coniferous forests in particular that move further north, higher in elevation during the middle Holocene, which is a relatively warm period. There's less seasonal contrast, and as we move towards modern, these tree lines receded. We've seen evidence of this all throughout the Rockies. If you see any of Patricia Fall's work from Colorado, that really hits on this point nicely over the last little while. So one key difference, of course, is that as we move into the future, we're really not going to be talking so much about insulation-driven climate change. We're going to be talking about greenhouse gas-driven climate change, which is a little bit different. So most of the records that encompass the last 10 to 15,000 years or so, those come from lakes. That's what I'm going to talk about today. But what we know a lot about, in contrast, of course, is this most recent sort of climate event, the Little Ice Age. This is where the majority of our tree ring records come from that tell us something about disturbance and to some degree nutrient cycling. Look at something like delta N15 in tree rings. And we also know from like some of Jeff Monroe's work in the Uintas just next door that we know something about tree line dynamics after the Little Ice Age. You can see that this is the Hayden survey, 1871. Engelmann spruce forests are a bit thinner, and you can see that they slowly move up in elevation towards present. We have a whole lot of archives from tree rings and from modern ecological studies and these sort of early survey parties that we can sort of interpret what our 20th century has been like and anticipate what the 21st century has been like. Keeping up with that idea, we've heard a little bit about this today, we have a lot of no analog disturbances that we can't really, at least this portion, we can't account for this in the paleo record. That's not really something we can see, but I think we can speak to how temperature, that as we sort of conceptualize or we couch on these emission scenarios like in the IPCC, we can anticipate how these changes to disturbance regimes might be controlled, modulated, modified by warming temperatures. And we know that we're losing ice, the rest of it might be extinct. We know that there are at least greater occurrences of more severe weather-related disturbances and greater contrasts in wetting and drying cycles that all influence the plant communities and disturbance regimes. In the West, I'd say some of the bigger work that's come out with these more recent records, this is 1970 to 2000, this is some of Tony Westerling's work, that shows a very strong relationship between the duration of snowpack and high elevation forests and the occurrence of fire. Okay? That's important to think about because that's something I'm going to draw on as I sort of try to interpret these paleo records from the past. Okay, so this is a site on the Aquarius Plateau. This is up near the Boulder Top area that is sort of this lunarscape of Engelmann spruce up here. And so I think this is a really fascinating place to visit it and think through what this might have looked like in the past. It's one of the most striking landscapes that I've visited in Utah because it's just so unusual. So it's heavily glaciated. There was about a 200-meter thick ice sheet on the top of this about 12,000 years ago. And you can see, I would argue that probably not a lot has changed over that time period. And that's where I'm going to get into that with the methods that we use, which are lake sediments. So this is a cartoon I made just to kind of conceptualize what a lake sediment record tells you if you're not familiar with them. So you have some basin at a high elevation, then you have a forest around it that's contributing pollen. That pollen is broadcast throughout the season into the lake. It becomes entrained in the sediments. Similarly, if you have a fire event, charcoal is produced, it's kicked up into the air and comes in contact with the lake surface, sinks. And so those settle into the sediments. If you ever had an introductory geology class, the law of superposition tells you, the oldest stuff is on the bottom, the youngest stuff is on the top. So when we take a core out of a lake, we essentially have a time series that's represented vertically. Consequently, if you're not used to looking at time on a y-axis, this is how quite a few of these figures will be, where time is zero, modern is at the top, and then older, progressively older going down. And so this is a completely made-up diagram, but this is just got to conceptually get at this. So this would be lodgepole pine, right, which we know is like a fire-prone species, a fire-adapted species. This is Engelmann spruce and subalpine fir, which we know sort of tolerate fire infrequently in comparison to lodgepole pine. And so there might be some abundance of lodgepole pine in the past that gives way to a spruce fir forest moving forward in time. This is a charcoal record, which we take all of these pieces of charcoal that fly into a lake, We count them, and then we use some statistical techniques to decompose the background charcoal values from the peak, or these what we infer to be a fire episode. And we can look at the magnitude of that event and get some idea about severity. And so that's what this figure is telling you here, is that this background charcoal is this little wiggly line, and then the peaks and the char values themselves are these spiky parts of the plot. When we decompose those statistically, this gives us what an event might be. And so from there, we can back out of that and look at frequency through time, which I think is an intuitive linkage with modern ecology, is to understand fire frequency. So altogether, if you look at the vegetation and the fire history together, we might say that, look, there was more fire, more frequent fire in the past when the forest was dominated by lodgepole pine, and then it became more infrequent as you move forward into it. Engelmann, spruce, and subalpine fir forest. This is what we do. If you ever see any people out there, we're not trying to get struck by lightning, holding big metal rods in the air. We are coring lake sediments. And these are all pictures from the Colorado Plateau, and that's what a typical sediment core looks like. So some of the sites I'm going to talk about today are scattered across three landforms. The Wasatch Plateau, which is a bit further north. The Aquarius Plateau, we have 2 lakes there. These are all over 3,000 meters, and then some lakes down here in the southwestern area of Utah on the Markagunt Plateau. Bryan Head Ski Resort and Cedar Breaks are there. You might have visited those. One of the motivations for this work, of course, was the spruce beetle damage. As you can see, these occurred in the 1990s at the Wasatch Plateau, Markagunt Plateau. But we have both modern and long records, and I'll talk about those as well as we go forward. So in case you haven't spent any time down here, and this came up a little bit today, but these are really strong gradients, both in terms of what they receive temperatures and precipitation. We generally have decreasing temperatures as you go up in elevation and increasing precipitation. We get a lot of orographically enhanced precipitation at high elevations. And you think about these communities that we've already heard about some today: sagebrush steppe, pinon, montane forest, subalpine forest that are mixed sort of here. And then we have a Krumholtz spruce zone, and then this is in the Tusher Mountain Range. We actually have tundra, this sort of alpine tundra up here. As we think about these through time, we know that climate is modulating both temperature and precipitation, which is going to control the organization of these vegetation zones, and they might have been different in the past than they were today. So the Aquarius Plateau, I'll start here. This is, that's Powell Point. This is taken from Bryce Canyon. Looking up to the north and the east, you can see it's sort of carpeted by this nice forest of Engelmann spruce and subalpine fir and quite a bit of aspen up there as well. It's basalt capped, it's heavily glaciated, and it has this bimodal precipitation regime, which is somewhat unique in the western U.S. It has this a big peak from the retreat of the Pacific storm fronts, all Pacific derived moisture. That's in the spring. That's why it's a great time to come to Utah to ski in the spring. And in the summer, there's a peak from the monsoonal precipitation that's basically convective storms that are enhanced with elevation. This is a Holocene reconstruction from Purple Lake. This was part of a paired site study from a lower elevation basin. And so what I'd like to draw your attention to here is, again, the time axis. This is about 9,000 years ago at the bottom. And what really surprised me looking at this is that throughout the Holocene, even when it was quite a bit warmer and potentially drier, that Engelmann spruce has essentially been parked at this elevation over the length of this record, over 9,000 years. As we move towards present, you can see that subalpine fir was pretty well represented there as well, and then becomes increasingly more important towards present. And I've heard quite a bit about aspen today, but if you think about this over the long term, at 3,000 meters, there's very little aspen pollen represented in this diagram, but as you get towards the top, it increases pretty conspicuously, I would suggest. So let's think about that in terms of fire, because we've heard a lot about aspen and fire today. So this is a charcoal reconstruction from Purple Lake. Here's the early Holocene again, strong seasonal contrast, lots and lots of charcoal. 3,000 years ago, no charcoal, which is not what you would expect with increasing aspen, right? If there's a linkage with fire disturbance and aspen becoming established. We have, these are the inferred peaks. Here's the frequency. This is episodes per 1,000 years. Fairly frequent fire, and then as we get into this last 3,000 year period, no fire at all. And so in fact, if you look at this core, once you get to about 2600 up until about 1850, there's not a single fragment of charcoal in the entire record from Purple Lake. Pretty interesting. And so the way that let me add this in there. So this is a photo of Purple Lake we took while we were coring, and you can see all that aspen in there. This is a fire that occurred in 1991, which is this most recent fire peak there. So aspen is regenerating when these stands burn, which is interesting, but we do not see that evidence of that over the last couple millennia. So the way that I was trying to interpret this was sort of using that Westerling model to think through, well, if we have these two dominant times of abundant precipitation that generally is going to reduce the flammability of fuels, how can we frame this and what we know about fire? So this is Fire Atlas data. This is by month. The histogram is area burned, and the fire is reported as this line plot here. And what you can immediately get a sense for is that from 1960 to 2010, that of course this landscape doesn't burn, right, when there's snow on the ground. So you can really see that what this snow-free period has been historically. What struck me is that the greatest, you could almost flip the histogram upside down and fit it in the precipitation histogram there. But what struck me is that the number of fires reported, these are just naturally ignited fires, occurs later in the season. And so if you've ever been on the Aquarius Plateau, you really start to get snow September and October. So if you think about that control, you need to extend the snow-free period in order to get more flammability on this landscape. And I would argue that must be what's happening here as we look further back through time, is that the arrival of later season precipitation as the monsoon, North American monsoon, was invigorated during the early and middle Holocene, that they would have prolonged the snowfall by a couple months and might allow us to get that sort of situation where we have greater burning taking place that we see evidence of here at Purple Lake in the early and middle Holocene. Interestingly, just as a side note, these are photos from Purple Lake that Steve Munson provided us. I went and tracked down the photo point in 2010 to take another shot. But that lake had a pretty severe spruce beetle outbreak. And even though that fire did occur in 1991, it didn't seem to really promote an intense fire throughout that watershed, interestingly enough. So just to quickly summarize there, I think it's interesting that the Engelmann spruce community seems to be pretty stable and resilient to a wide range of fire regimes over the last 9,000 years. It has managed to remain the dominant tree type in this landscape despite this considerable variability in fire regimes. Okay, this is the Markagunt Plateau. This is the one down in the southwest. This is a really odd landscape. It's a volcano karst. It has relatively recent lava flows. These are about 1,000 years ago. And then there's limestone underneath that. So there's lots of unique geologic features if you go down there, plunge pools and lava tubes and all of these things. Again, you can see this, a pretty similar precipitation distribution throughout the year. The spring precipitation and the monsoon signal there. This is the terminal moraine of the glacier that was there, and this is a little dead ice block lake that we cored. That's just a shot of the landscape. And so this is a bit higher resolution record than the Purple Lake record I showed, but you can see a very similar story down here in the Markagunt. Lots and lots of Engelmann spruce throughout the Holocene. A little bit less subalpine fir that increases towards modern, which we also saw in the Aquarius Plateau site. And again, populus right here is a little bit more present on this plateau, but it also becomes, it increases towards present. Okay, and just to get real quickly into that, this bottom profile is our proxy for the North American monsoon. And this here is Chris Moy's record of INSO. And you can see that these, what I would say, particularly if you check out Douglas fir right here, comes into this record. And it might have a little bit to do with this change in the seasonality of precipitation, where there's essentially a collapse of the summer precipitation regime there. Again, with the fire reconstruction, a lot of variability. But you can see a general decrease in the last few thousand years relative to other areas, particularly the early Holocene. But this area in the middle Holocene is intriguing. don't know much about that yet. Okay, so really quick, I think I have just a few minutes left. Okay, I want to get to one other thing, which is we know a lot about bark beetles, so I'll kind of get through this pretty quickly. But I'm going to be talking about spruce beetle and its effects down here and some of the work we've been doing. That's basically, bark beetle outbreaks are increasing because of warming temperatures allows for faster reproduction and greater overwinter survival. But another thing that I'm particularly interested in is in the role of forests and what have we done to forests that have exacerbated this outbreak. So if we think about a normal outbreak that would infest this is the host, non-host. Let me get through this quick, though, get to the juicy details. So these are stand inventories of blue and emerald lake. And what we've done here is taken pollen accumulation rates here and biomass reconstructed from the stand level surveys to look at the settlement history of this basin, see what's happened. So this is 1700 AD to present. And interestingly, what happens is that we see a big crash in the Engelmann spruce that's probably related to settlement era logging. We know that from records that are from the Wasatch Plateau. This is one of the most adversely affected landscapes in all of western North America from logging, and kind of leads us to propose a conceptual model here of how we could have two different pathways that result from anthropogenic logging disturbance during the settlement era that lead us to very different outcomes here during the 1990s when these outbreaks have been associated with climate warming. So I'll stop there. I think that's probably about all the time I have.
Had gotten as far as interactive effects of the spruce beetle and the fire over this long time span. Have you looked at those things, how they work in combination with each other?
Yeah, that's an interesting question, and that's something that has remained somewhat elusive, but we've tried to, one way I've looked at that is using that same index that I showed you in this slide here, using this same biomass and this threshold idea that when landscapes become susceptible, that we would expect an outbreak rather than looking for the outcomes of that, if you will. Looking for what the susceptibility is. And interestingly, I don't have this charcoal plotted, but this period where stand density, this is time here 13,000 years ago, between 6,500 and 2,500 years ago is the only other time in this entire record where we see inferred stand density anywhere near as high as it has been in the very recent period. The charcoal record, this is the most abundant charcoal of this entire record, though I don't have it plotted here. So it seems to suggest that at least with contributions of woody fuel, maybe that's producing more charcoal when these do interact.
That if there was a large beetle outbreak, is there necessarily a fire charcoal peak following that, or have you gotten to that level of?
I don't think we can speak to that at this time, simply because the resolution of at least from the pollen that I showed you, these outbreaks, maybe they show up for 10 or 20 years, which is why I've switched over to looking for the susceptibility conditions rather than the outcome. If that makes sense? Like if we were going through a record and looking for an indicator of an event, which is what we do with charcoal, when we see more charcoal, we say there's a fire. But if we look for the outcome of an outbreak event, we don't see the same thing because the temporal resolution of our cores can't allow us to speak to like a 10 to 20 year change in the pollen ratio. There's no direct indicator. Whereas we know there's charcoal when something burns. Did that help at all? Or? Get there, okay, maybe.
It sounds to me like it's a temporal resolution issue.
It is, but it's also the fact that we don't have a direct indicator of the outbreak like we do with charcoal. Because we can overcome that with charcoal, because we can count it and we see that it's more at one point in time. But with pollen, there's this sort of, it grades through time. It self-attenuates. Yeah.
By you not finding aspen early on in your first site, especially, has the climate, from your records, I'm assuming you will have to speculate on that, but has the climate changed that much compared to
winters were probably quite cold, but the summers were substantially hotter, like in the earlier portion of these records. But I think, I mean, I didn't mention it, but if you look at some of the work that's come out of Colorado from Leslie Anderson, and she's looking at oxygen isotopes in these subalpine lakes in the Colorado Plateau, and what she shows is that over the last 3,000 years, there's a significant stepwise increase in snowpack. And that is exactly when, at the same time that we see aspen increasing at these high elevation sites. Yeah, so maybe it's a water, I'm not sure, it'd be pure speculation, but there's certainly a linkage there with climate that it's suggestive, yeah.
More questions? Join me in thanking Jesse.